Let us consider field patterns. For a loop gain, for a loop of given size, beta A is constant and the field pattern so depends upon the Bessel function J1 C lambda sin of theta, where C lambda is the circumference of the loop. Therefore, C lambda is equal to C divided by lambda. So, this is equal to 2 pi A by lambda. So, this is equal to beta into A. The relative fields, so depending upon the function J1 into beta A sin theta, it is shown in the figure. So, that is the relative field of an antenna which is depends upon the Bessel functions is shown in these particular figures. Now, the Bessel functions for a small loop approximately of size C lambda is less than 1 by 3 is equal to J1 of C lambda sin theta. This is equal to C lambda sin theta, and this can also be calculated from the equation pi A divided by lambda sin theta. That is J1 into C lambda sin theta is equal to C lambda by 2 sin theta. This is equal to pi A by lambda sin theta. Hence, for a small loop, the fields could be, that is for a small loop antenna, the electrical field component and the magnetic field component are calculated from this equation, and it is calculated from this equation. That is, electrical field component is calculated from this equation and the magnetic field component is calculated from this equation. Let us calculate the radiation resistance. For small loop antenna having the size A is less than lambda square by 100. For a small loop, h theta is equal to pi into I0 sin theta divided by r into A by lambda square, where this I0 is the current I and the power radiated is a double integration P RMS into ds, and this P RMS is equal to 1 by 2 E theta into H phi. into ds, and so this you can write it as 0 to 2 pi 0 to pi 65 s theta square r square sin theta d theta. That is, your ds is equal to this r square sin theta d theta, and 1 by 2 e theta h phi you can write it as 65 into s theta whole square. In terms of radiation resistance Rr, Wrms is equal to I square Rms into Rr, and this I square Rms you can write it as I0 divided by root 2. Then equate equation number 11 and equation number 12. Then Rr equal to 31,200 into A by lambda square, and if antenna contains n number of terms, then Rr equal to 31,200 A into n divided by lambda square whole square, and this equation is used to calculate the radiation resistance. consider a larger loop. Larger loop means where the size of the loop antenna is greater than or equal to the wavelength of the signals. The RMS power density is given by 1 by 2 h square into 120 pi. So then these 2 and 120 will get cancelled. Then Prms is equal to 1 by 2 h square into 120 pi, and this equation becomes 60 pi into h square, and this is equal to 65 into s theta square. So now substituting h theta from the equation number 10, that is, here you have s theta, substitute the values of s theta from the equation number 10, then Prms is equal to 15 pi BA, Prms is equal to 15 pi beta A I0 whole square divided by J1 square beta A sin theta. Then the total radiated RMS power can be calculated from the equation. WRMS is equal to double integration Prms into ds, and here you have the Prms, substitute the values of Prms, and ds is sin theta d theta d5. Then this equation is simplified to 30 pi square BA sin 30 pi square beta A I0 square. This is equal to 30 pi square beta A I0 whole square 0 to pi J1 square beta A sin theta d theta. Then from the property and the Bessel functions, okay, now from the property of the Bessel functions, you can write 0 to pi J1 square x sin theta into sin theta d theta is equal to 1 by x 0 to 2 pi J2y into dy. Then apply the equation number 15 concept to the equation number 14. Then we can write this WRMS equal to 30 pi square beta A I0 square into 0 to 2 beta A J2y into dy. And now putting C lambda is equal to B into A, then WRMS is equal to 30 pi square C lambda into I square 0 to 2 beta A J2y into dy. Then we will equate this power to I0 by root 2 whole square into RR. Then the radiation resistance is equal to 60 pi square C lambda 0 to 2 C lambda J2y into dy. And for a single turn and a large loop antenna, that is, antenna contains only one turn and the size is very large, then integration from 0 to 2 C lambda J2y into dy, the value is equal to 1. If this is equal to 1, then this whole term becomes equal to 1. Then radiation resistance is equal to 60 pi square C lambda square. Okay. Then, so this can be further simplified to 592 into C lambda square, and this also you can write it as 3720 into A divided by lambda. So this is how you can calculate the radiation resistance. Now let us see the directivity of loop antenna. For small loops, the directivity is equal to 1.5, and for larger circular loop, directivity equal to 4.25 into A by lambda, and this is equal to 0.68 C lambda. Now let us study some applications of loop antenna. First application is used as a source for paraboloid type of the antenna. Second one is an array of loops of different sizes or the dimensions can be used for line of sight communication. Third one is it can be used for omnidirectional system, and fourth one is it can be used for directional finder. Let us solve some problem on loop antenna. The first problem is a radius of a circular loop antenna is 0.02 lambda. How many turns of the antenna will give you a radiation resistance of 35 ohms? Okay. Solution: A equal to pi into 0.02 lambda whole square, and the system is said to be small circular loop, then A must be less than lambda square by 100, or A by lambda square must be A. The system is said to be small, therefore A is less than lambda square by 100, or A by lambda square is less than 0.01. For a given system, A by lambda square equal to pi into 0.02 whole square, and this is equal to 0.001256, and this value is less than 0.01. Therefore, the given system is small loop. Then the radiation resistance is calculated from the equation RR dash equal to 31,200 into AN divided by lambda whole square, and this radiation resistance value of 35 ohms is given, so therefore it is equal to 35 ohms. Then substituting the values, here you got A divided by lambda square. A divided by lambda square is 0.001256. So that value you are substituting it here, A by lambda square, and that n remains as it is. This is equal to 35, and from this equation n equal to 26.7. Therefore, rounding it to the nearest integer, this value equal to 27. That is 27 turns of the loop antenna will give you a radiation resistance of 35 ohms. Let us solve one more problem. Find the induced voltage in vertical loop antenna of 20 turns due to field strength of 20 millivolts per meter at 2 megahertz frequency. The area of the loop antenna is 1.5 meter square. The given values are E RMS equal to 20 millivolts per meter. So, this is equal to 20 into 10 to the power of minus 3 volts per meter. Number of turns equal to 20 and frequency is equal to 2 megahertz. This is equal to 2 into 10 to the power of 6 hertz and area is equal to 1.5 meter square. Then the RMS voltage induced in the loop antenna is given by V RMS is equal to 2 pi into Em into An cos phi divided by lambda, where phi is the angle between the loop and direction of the incident wave, and that value is equal to 0. In this equation, substitute all the values, then you will get the value equal to 35.543 millivolts, and this is the induced voltage in the loop antenna. Let us solve one more problem. Find the directivity and radiation resistance of loop antenna with a diameter of 1.5 lambda. D equal to 1.5 lambda. Therefore, A equal to radius, so this is equal to D divided by 2. So, this is equal to 1.5 lambda divided by 2. So, this is equal to 0.75 lambda. Then C by lambda is equal to 2 pi A by lambda, and this is equal to pi D by lambda. Pi D is 1.5 lambda divided by lambda. So, therefore, lambda and lambda will go, we will get left with 1.5. Here C by lambda value is equal to 1.5 lambda, that is greater than 1 by 3. Hence, this is a larger loop antenna system, and the radiation resistance is given by RAD equal to 3720 into A by lambda. This is equal to 3720 and A value is equal to 0.75 lambda. It is calculated here. Substitute it and pi will go left with 2790. So this is the radiation resistance. So then the directivity is given by D is equal to 0.682 C by lambda. This is equal to 0.682 C by lambda is calculated here. So this is equal to 1.5, substitute 1.5 here. So then it becomes 3.2185. This is the directivity. Solve one more problem. Find the radiation resistance of a circular loop antenna of radius 0.3183 meters operating at 1 megahertz. The radius of the wire is 0.4 mm and the conductivity of the given wire is 57 and mu r equal to 1. And for this problem we have to find the radiation resistance, and the radiation resistance is given by RED equal to 197 into C by lambda raised to 4, where C is equal to 2 pi A, this is equal to 2 pi, A value is equal to 0.3183, it is given in the problem. So this is equal to 2 meters, lambda is equal to C by F, C is equal to 3 into 10 to the power of 8, F is equal to 1 into 10 to the power of 6, so this is equal to 300 meters. Now substitute all the values in this equation, therefore RED equal to 197 into 2 divided by 300. So this is equal to 0.3891 into 10 to the power of minus 6 ohms.